travel a bit far, and I couldn't make back to Nairobi. So I decided it's good to still have the class online. And we're just going to, sometimes I get busy and forget what I did in the previous class. And your class rep never reminds me. Whenever, like, I was to send you some work or some table to do the calculations, get the limits, the control limits. So that was supposed to have happened last week. But all the same, we will just go through. So let me share something here. So I bet you can see what I'm sharing. Can you? Be able to see what I'm sharing?
Yes, we can see.
Okay. So I introduced the X bar and R charts in our previous class. And our focus will actually be on these, the X bar, the R charts. That is for the variable control charts. Then you also be looking at the P chart and C chart for attributes, the control charts for the attributes, and we'll be seeing what they entail. So we did introduce the X bar chart, and basically what it entails. So all these I'll be sharing these PDF afterwards, because some of these things we don't need to actually write down. We can read them from the PDF, and that is it. Getting to know can allow me just a minute. Okay, sorry about that. So I was talking about what actually the X bar chart entails. We can see it shows changes in process average and is affected by changes in process variability. So this is basically what we were considering, the standard deviation. So standard deviation, we get standard deviation from the variance. So that kind of variability is what helps to measure or determine whether a process is actually within or outside the control limits. And basically, we also use the X bar, and you know that is a measure of the central tendency. So all these I'll be sharing so that you can just go through the notes. Then we also talked about the R charts. So R, in this case, range, R will stand for range. And we know that range is basically the difference between the maximum and the minimum, or the largest and the smallest value. In this case, when you are given a set of data, then from each of the samples, you can be able to identify the largest value. You can also be able to identify the smallest value. And so it will be easy for you to get the range for each data set. So now where we were supposed to go next was now about protein. So I illustrated a general control chart, what it entails. That is the the upper and lower control limits. And we gave a bit of the mathematics involved. So when we talk about the X-bar chart, so you have several samples, and from each of the samples, you get its mean. So you can have, say, 10 samples. So those 10 samples, they have a data set, possibly of 5 values each, 4, 7 values, and so forth. And so you get the mean of each set. Then once you get all the means, then depending on the number of samples you have, you add all the means, then divide by the number of samples that you have. And that is going to give you now what we have here is X bar bar, which simply means or implies it is a mean of the means. Then again, from each sample, you calculate the range, that is getting the smallest and largest value from each, then you get the range. So depending on the number of samples you have, you get all the ranges, then you get a mean of the ranges. That is now adding all of them and divided by the number they are. So you can appreciate these are actually the formulas, or these are we illustrated how we get the control limits for the X bar, the upper control limit. We have the X bar. So I think I didn't add the other bar, but simply mean it implies you have to get the mean of the means because you have several samples. So from each sample, you have to calculate its mean. Then from there, you get, you add all the means, divide by the number of samples you have. And then you add the A2. And remember, A2 was coming from where we were estimating the standard deviation. And so we got this as the last formula for the upper control limit, the lower control limit. Then the control limit, that is now the EQL. Okay. Then for the R chart, again, we saw these were the formulas that we got for each, that is for upper and the lower control limit. Now, to note that we actually have, just like from the business statistics one, we talked about the statistical tables. So the statistical tables are always, those are values which have been calculated a long time ago. They were estimated and they were actually verified to be representing a certain value. So when you're talking about the student T, when you're talking about the normal distribution table, so those tables will always be like that. So when it comes to control charts, or basically in statistical control quality control, we also do have a table that has all those constants, the A2, the D3, D4, D2. We also saw the case of C4 and so forth. Now, all those, again, are already tabulated. Now, depending on your sample size, where N now is the sample size, depending on that sample size, then you can be able to get to know which value of A2 are you going to consider. So if your sample has 10 values, then the A2 that you pick is the one 0.308. And the same case applies now when you're doing now the R chart. Then you consider for the lower control limit, then you have to know which D3, again, depending on the sample size that you have. And therefore, so when it comes to now to having an example, we have an example here. So this is an automotive engine. So where they are actually manufacturing pistons. I don't know if you know what pistons are, but then this is the kind of data they collected. So they have 25 samples, and each of the sample has 5 values or 5 observations. So we have the number of samples. Sorry. We have the number of samples here, that is 1 up to all the way up to 25. Then each sample, if you check across, each sample has 1, 2, 3, 4, 5. 5 observations up to this point here. Up to that point, we have 5 observations. And therefore, so what you're supposed to do is to add all these. You add each of these observations. Then once you add them, they are 5 of them. So eventually you divide by 5 so that you can get now what you have here, the 74.010. So that is the first mean for the first sample. Then you do the same. You have the second sample here. So all these values, again, you add them up, then divide by the number they are, that is 5. Again, you get its mean. So you do that for the rest of all the samples. Now, this is just an example. In most cases, we do not, even in an exam setting, we do not give so many samples. We only give a few, possibly 5 for that case. So for each, you'll be getting the sum, divide by the number they are, get to the mean, and so forth. And so now, eventually, once you are done getting all the means, you then, so once you're done getting all the means, you then now calculate here. Then now calculate the mean of all of them. Okay. You get the mean, you sum them, then there are 25 of them in this case. So the 1850.028, that is the sum of all the means, then divided by the number they are, that is 25. So you get the mean of the means to be 74.001. Then you do the same for the range. So here, go back to where you have the range. So again, here we are getting the range for each of the samples. So from this you identify which is the largest value among these for the first sample. Which one is the largest? Yes?
74.030.
The 74.0.
74.30.
This one, the first one. Right? And the smallest value?
Yes.
The smallest value?
73.992.
The 992. Okay. So if you get now the difference between the largest value and the smallest value, so you can confirm whether it gives the 0.038.
0.038. Yes.
Exactly. Okay. So you do that for the first, again, the first sample. Again, you identify from the second sample, again, you identify the largest value among the 5 that you have here. So that is which value? Which value for the second sample? Which one is the largest?
74.011.
011. And the smallest? So again,
73.92.
992. Okay. So again, you take the difference, then you realize again it is 0.019. So you do that for all the samples. Do that for all the samples up to the 25th, or depending on how many samples you have, and then add them up. Then what you get, like in this case, 0.581 divided by 25. And again, you can confirm whether that is the case. So whatever you get, divide by 25 to get 0.023. Right? Are you getting that?
Yes, it's correct.
Okay. So now, once you have those two values, that is the mean of the means, in this case 74.001, and the R bar, that is the mean of the ranges, 0.023, then now you can easily now apply the formulas for the control limits. And I said that in most cases, instead of providing the tables, we just give you the values for the constants, the A2, the D4, and the D3. So instead of giving out the table of the constants for the SQC, we give the constants. And therefore now you can easily get the control limits for the X bar. So this will give you the control limits for the X bar. So you can see we have the mean of the means plus the A2, then R bar. So you get that. Then the lower control limit, again, so now here we subtract. So we have A2, again, R bar. And then this will give you the 73.98766. So that is to say that whatever you get as the average from each sample should not exceed on the upper side, it should not exceed 74.01434, and on the lower side, it should not exceed or go below the 73.98766. Okay. Then you do the same, again, apply the formulas for the R chart to be able to get the control limits. So we said the upper control limit is D4 R bar. So here it is multiplication. So again, you have the constant for the D4 and the R bar, got it up there. So you get this. Then lower control limit, the D3, which in this case is 0. It is 0 for the case of just 5 observations in every sample. And then, so that will automatically be 0. And so now, once you calculate that, then now what remains is you now plotting the charts. Plotting the charts. Now, what you need to know here is that we have, like we said, we have the upper control limit. You've gotten the value. You have the lower control limit. You've gotten the value. And then you have the equivalent quality level. It is this center line here. The center line, which is basically the mean of the means that you've gotten. Now, here, what you have on the y-axis, possibly we can refer to that as y-axis. What you have on y-axis are actually the sample means. All these, they're actually the sample means, the ones that you have calculated on this side here. All these, you can, so all these, let me just highlight so that you can just, so all that the sample means, all of them, depending on how many you have, then those will be the values that you actually have on the y-axis. Those are the values that you have on the y-axis. Therefore, you'll be plotting now these control limits, the control limits, then the number of samples that you have. So from sample one, you can see that we got the mean is 74.010. That is the mean of the first sample, 74.010. Then you go to the second sample, its mean, again, you check, its mean is 74.001. Then if I go to the last one here, 25th, is actually 73.998. So 73, so if you locate 73.998, you can see the last one here, it is approximately that point, 73.998 somewhere. And so that is the 25th sample. So all the dots that you can see here are actually the values of the sample means. The sample means. So all these. And then now you connect from each sample, the first sample to the second sample, you connect it with a straight line. To the third sample, a straight line. That. So you'll be looking at all these deviations from the center line here, because this is what the company expects. So if it is the amount of, or rather, the weight of a bread, which we said is 400 grams, that is the standard. So they'll be having that against all the samples that they will collect, they get their means and see possibly one bread will be 405, another bread will be 395, and so forth. So that deviations will tell whether the process is actually under control. And they give allowance. So the control limits that you have calculated are actually the allowance that you can give for such deviation. So if at any point, like you can see this was almost going outside. If it happens to go outside this, then eventually that process is out of control. It is not under statistical control. And therefore, what will happen, it is either you again go back, destroy everything, and start all over again. Or else, consider all the other samples and see what is the deviation. And maybe it is only that one sample which has some issues. And so you can do away with that sample alone, then allow the others to just go into the market. But that is what you don't know is that because these are again samples, the larger part of production is still in the store. And so what would happen if this was actually a good representative? Whatever is going outside, maybe it's the best representative of what the whole production or the whole process produced. Then you'll be having some defective items going to the market. And that might not be good because customers might realize that they are getting bread which is only 390 grams. And so the company might lose some customers in the process. Now, again, when it comes to so this is the same case here. It's only that it is a bit squeezed, but so this is the same as what we have up here. But now consider the range, the range or the R chart here. So the R chart again, so we have the groups or rather the samples. So from each sample 1 all the way to 25, then you plot their ranges, the ones that you got, the ranges. So against what you got as the center line or the EQL. And therefore, once you go back to where you have the ranges, you can see we have the ranges here. So for each sample 1, you plot its range. So it is 0.038 something. You can see it is not up to 0.04. Then if you go to the last one is 0.035. So the 25th is 0.035. So again, 0.035. Again, you can see it is somewhere there in the hydro. And so you'll be plotting this so that now you can again check. We do have the lower control limit as 0 because we multiply the D3 was 0. So D3 multiplied by R, we got that to be 0. So the lower limit. And in most cases, again, I like to also again put it that when you get the lower limit as a negative, because sometimes you might calculate and given the constant that you have and you get this to be a negative. So we don't include the negatives. We only include up to where you have 0. So 0, then upward. So whenever you calculate and you get a negative, then just limit it at where you have 0 on the lower side. Then, of course, on the upper side, that one is left open up to whichever value you calculate. In this case, we can see that we got 0.04. Yes, 0.04853 is the upper control limit. And basically, that is how you just get the control limits. So you'll be taking a sample from whatever you've produced. Get, if it is measurements you're taking, it could be even not just weight, it could be height, it could be length, it could be all that. It could be the amount of ingredient, it could be all that. So what you do is you just ensure that you get the average of each sample, then get the average of those averages now. And then now use the mathematics to get the control limits, like in this case. Then the control limits will be where now what is allowed, up to what extent can you have that deviation. Then now you can plot. So once you plot, then you can now interpret that with respect to the information that you've gotten from your graphs. So like in this case, we can see in the X bar chart, all of the time, the plotted points represented average are well within. They are well within the control limits. So that is what you've seen in this case here. All of them, none of the points is going outside the control limits. And if that is the case, then we are saying, but if some samples fall outside the control limits, then it means something has probably gone wrong or is about to go wrong with the process. And a check is needed to prevent the appearance of defective products. So if it is the bread, if at the point you measure, you realize that you're getting 4 or 5 grams, then in terms now of control, the quality control, that one is considered defective because it is not what is written there or the standard that is required. So what will happen? It is either, of course, some will just choose to sell the way it is, but you need to go back to the process and identify where are you getting it wrong. If we have unqualified personnel, then you need to do away with them. If it is the machine, maybe the one that is cutting that bread, you need to relook to that and so forth. So we have a complete table here of the constants. Don't know if we have a question up to that point. Is it have you understood how you go about it? Yes, members, is it clear?
Yes.
Okay. So I'm saying we have a complete table here of the constants. So like I said, just like we have the statistical tables, we also have the statistical quality control table for the constants. And these, they are already tabulated. They have already calculated. We said this depends on the sample that you have. You can see the mathematics they apply to calculate some of these, the A3, the C4. But this one, at this level, we do not need to know how you calculate all that. So what we just need to know is how we can actually be able to get the control limits given those constants. And I said we normally do not provide this table, but I'll share, you will still have it. But in the exam, possibly what you get are the values for the A2, the A3, or the C4, the D4, and so forth. Then we can talk about when the process is out of control. So what actually has happened, if you say that a process is out of control, it possibly have faulty tools. So the machines that you're using, the cutting machines, maybe they are faulty, and so you need to have them relooked and make some adjustments or buy new ones and so forth. The materials that you're using, they could also be having an issue. There could be an issue with them. So maybe you have changed your supplier. So once you change your supplier, then things might not be as usual. So you have breakout maybe from the system, or even the timing. So like I said, even the refilling of bottles, the soda and such, they are timed so that you don't maybe refill halfway or even have it spill over. So you have to be careful, you timing how you refill 300 ml. It is timed different from how you refill 1 liter and so forth. So those are some of the things that could be the problem in your process. Therefore, you need to work on them. So a process is in control once you compare the specifications or the standards that have been set on, and what you get as the outcome. Then at that point, if they concur, then you can say the process is in control or under control. So you compare the two and see whether they actually concur. And so basically that is how you do the X bar and R chart. So for the conclusion bit, you just conclude whether you, according to your analysis, whether it is under control or out of control. And basically for someone who is now an expert in that area, will give recommendations on what can be done, or do they need to again go and check the machines? Do they need to revert to the previous supplier and so forth? So that is basically how you do it. And for this case, we are just, because this is just one of the units, if you are doing a course that maybe you end up becoming an expert in that area, there is a lot more that possibly you need to cover, including the quality assurance and so forth. So now, like I said in the beginning, we have control limits or control charts for variables, that is X and R. You also have control charts for attributes, and you can see attributes are used to measure quality characteristics that are counted rather than measured. So, like I said, in the height, the weight, that is something that you can measure. But if it requires you now to count, maybe identify the number of defectives and so forth, then it will need you to now consider having a control chart for attributes. And so in this case, we have, like I said, we have two of them, two major charts. that is the P charts. And from its name, the P standing for proportion. So proportion is basically a number out of another. So the proportion of broken cookies in a batch, the proportion of cars produced with a misaligned fender, and so forth. So once you're able to determine the number of defectives, maybe from a sample that you have, then you can apply now the P chart to demonstrate or to illustrate whether the process is out of control or under control. So now, how do you go about plotting? Because that is mainly what is of interest here. So you first calculate and get the fraction defective. So if you have produced 100, then you must count to see how many out of the 100 are defective. So if you have 10, then that will be 10 out of 100. That will give you now that proportion. So you can see it is a fraction. So a fraction, we normally know that that is something that is less than 1. In case of a process is out of control, then something needs to be done. So how do you get now the mean proportion defective? So we are saying total number of defectives out of total number of items which are inspected. And I'm not quite sure whether this formula is new to you, but in tests of hypothesis, we have tests for proportions. I don't think we went to that extent, but we do have tests for proportions. And this is actually the formula that is used for the standard deviation when you're considering proportions. So you can see the P with a bar is right here. So the standard deviation for this, or what is the deviation from the required, will be now the square root of P bar into 1 minus P bar. And we have said P bar is a fraction. That is why once you take 1 minus P, it will also be a fraction. So you cannot not get a negative. You cannot get a negative, especially inside the square root. If you do, then that is a different area where you have negatives inside. Even your calculator cannot be able to calculate a negative square root. So then now, how do you get the control limits? Simply like in the other cases of the of the X bar and the R chart. So we have the P bar, which now in this case we are considering to be the EQL, or where now the center line will be. Then that added to Z. Now I'll be telling you what Z is, times whatever standard deviation you have gotten here. Now, in the test of hypothesis, we refer to this as the standard error. Standard error, or meaning just the standard deviation, the deviation from what is intended or what is required. And so for the upper control limit, we add the Z. So Z is from the statistical tables. The Z, we get that from the statistical tables. Then if it is the lower control limit, then we have, you subtract. So of course, we already know what is sigma P bar, because it is calculated here, the sigma P bar. So that is what you have here. And therefore, with that, you can easily, these are even straightforward. You can easily be able to get the control limits for that. So we are saying if you have a sample, we've said if you have a sample of 100 items, then from these 10 of them are defective once you count them. So that will be your P. And therefore, so that will just be 1 out of the 10. Then Z, you're going to see how you calculate that, or how you determine that Z. But in most cases, because we are considering this to be a normal distribution. The values that you get, the number of defectives out of the total that you get, we are considering this to be a normal distribution. And therefore, in most cases, the value of Z is usually given as 1.96. 1.96. That is, now this is a value that is already tabulated from the normal distribution. And then, of course, so the 1 over 10, so into, so you can see that 1 minus 1 over 10, so that will again be 9 over 10. And you can, now depending on n is the sample size. So n in this case now will be the 100 that you have. That will give you the n for that case. And therefore, with the knowledge of all that, then it will be easy for you to get all those control limits and be able to plot that very easily. And so I'll be sharing an example. I think, let me see if I have an example here. So I'll be sharing example. Then now, what I want you to note, the if you take 1.96, we are considering this a two-way on. Let me just demonstrate that. I don't know if you recall the normal distribution table. So this is where you have the 0. If you can recall the normal distribution, then we say that this is the rejection region, and then inside here we have the required region. So on either side, we are saying that this value here could be 1.96 approximately, and this side here could be negative 1.96. So now all this is approximation. And therefore, since it is just approximation, so we take this side and this other side here, okay? If you multiply the 1.96 times 2, how much do you realize for that? It is around 3.92, okay? But since it is an approximation of that, so that is basically almost up to 4. So that is the 1.96. If you were to round off, then that is times 2, that would be 4. But then we do not want to go up to that or that, because 4 is actually the whole of this side goes up to 3.9. So most cases they give up to 3.99, and this side again up to negative 3.99. So To avoid having it as 4, we just limit this to 1.5 on either side. 1.5 on either side, and therefore the value of z now becomes 3 in this case. The 1.5 times 2, which should be now the required deviation from, if you consider either of the sides, then we mostly put that to 3. So since the variations within 3 standard deviations are considered as natural variations. So now these are not mathematics. We are even interested in doing, but just to get to know where the 3 is coming from. So it is something that has already been passed as standard. You see, a natural variation. So that term itself, natural, it means that everyone has accepted that that should be the value of z. So, however, the choice of z, value of z, depends on the environment in which the chart is being used and on managerial judgment. So you see, I've said in most cases, we limit that to 1.5, 1.5 on either side. But others will just choose to have it as 1.96, 1.96 on either side. Okay, and that now will be 3.92. But so whoever is doing this might consider to just have the value as whichever value they want. But in our case, let's just work with what has been passed as standard, and that is 3. And so now, having calculated the value of the p bar, then you know that now z is 3. Then this one, you can now get it from this relation here. Then once you get that, so what remains is you now drawing. So and we are going to see what do you draw against what. So if you have your control limit, so this one here is the p bar, then you'll be selecting several samples. So you have a sample 1, you have a sample 2, all that, depending on how many samples you have. And so from each sample, you'll be getting its p. So that is the fraction of the defectives from each sample. Then, so again, you'll be able to plot again a similar control chart, like in the case of the X and R bar. So in this case, you have an upper control limit. For that case, you also have a lower control limit. And I've said in most cases, you realize that this might be negative, and therefore you just limit it to where you have 0. And then, so that is basically the P chart. So what happens in the C chart? Again, another straightforward chart. So C charts, again here, you count the actual number of defects. For example, you can count the number of complaints from customers in a month, the number of bacteria in a petri dish, the number of barnacles on the bottom of a boat. However, we cannot compute the proportion of complaints from customers. Neither can you be able to know actually how many bacteria are there. You can you can tell how many have you seen, but possibly you may not know out of what you've seen, how many are even outside there, and so forth. So because we cannot take the proportion, so what we just consider is now the number of defectives that you have. And in this case, I just want to take you to where you have the formula. So we are talking about getting the control limits. So this C bar here, it is the total number of defects that you can observe, then total number of samples that you have. So total number of defects divided by total number of samples that you can realize. And then that, if it is now the upper control limit, then you need to add plus 3. So you already seen 3, where the 3 is coming from. And then the square root of, again, the C bar. Then if it is the lower, then you need to just subtract the C, so number of defects divided by the total number of samples, then minus the 3, again, square root of C bar. And you say that sometimes this might be, what you get here might be greater than what you get as the C bar, and therefore your lower control limit will just be 0 in this case. And so what is now the difference of this? So we are saying the P chart is used on both the total sample size, the sample size, and the number of defects can be computed. So you can already be able to get the sample and the number of defects from each of the samples. But when it comes to the C chart is when we can compute only the number of defects, but cannot compute the proportion that is defective. Why? Because we might not be able to get exactly what is the total sample size. We can only be able to know how many defects can we see, can we observe. But we don't know what is the sample size, or we cannot even get a sample in some cases. We don't get the samples. And therefore, with that difference, then you can be easily differentiate the two. And I'll be sharing, because I don't have the examples in this PDF, I'll be sharing that, the C chart, the P chart. And again, if you go over the internet, you can easily be able to get or to see how do we go about the P chart, how do we go about the C chart, and so forth. Now, again, also to mention these 3 here, don't know if I mentioned about it, I think I mentioned about that. So we talk about the 3 sigma, the 3 sigma control charts, the 3 sigma control charts. Now, that is why in most cases you realize that you have these 3. So whenever you come across a question that requires you maybe to calculate the 3 sigma, just know they are talking about the 3 sigma because we are considering the value of Z to be 3 in all these cases that you have. So control, maybe the question that you have the defectives and you have the sample size, but they are telling you now to get the 3 sigma control chart. So it is upon you to know, because those are the defectives and you can see the total number of items that were inspected, then you definitely know it is going to be a P chart. It's only that now the value of Z will actually be equals to 3. To be equals to 3. Therefore, with that, I don't know if you have any question. Any question up to that point? Are we good? Yes?
Yes.
Okay. I was